Welcome everyone. I'm excited to kick off our presentation today on gravitation. This is our first slide, and I want to briefly introduce what we'll be exploring. We'll cover the fundamental concepts of gravity, its significance in the universe, and how it influences everything around us. So, let's get started and delve into the fascinating world of gravitation. Let's take a quick look at the contents of today's presentation. We will start with an introduction to gravitation, which is the fundamental force that governs the motion of planets, stars, and even objects on Earth. Moving forward, we'll explore the importance of the universal law of gravitation, which explains how all masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. We'll also examine the factors affecting the value of g, or gravitational acceleration, which varies depending on location and altitude. Understanding how to calculate g is essential for many practical applications, and we'll see how this plays out, especially when considering the weight of objects on different celestial bodies, like the moon. Throughout the presentation, we'll delve into concepts like free fall, centripetal force, and the distinction between gravitational constant g and gravitational acceleration. G will explore the mathematical expressions that describe these forces, helping us understand how they relate to real-world phenomena. Finally, we'll compare mass and weight, clarify their differences, and conclude with some key takeaways. All these points tie together to give us a comprehensive understanding of gravitation and its significance in physics. Let's start with the basics. Gravitation is the force of attraction that exists between any two objects in the universe. It's what keeps planets orbiting the sun and moons circling planets. Now, a simple way to understand this is by looking at Earth's attraction. For example, if you drop a body from a certain height, it doesn't just stay in the air or float away. Instead, it falls downwards, and that's because of Earth's gravity pulling it down. This force is what gives us weight and keeps everything anchored to the ground. Throughout this presentation, we'll see how this fundamental force influences everything around us, connecting the dots between celestial bodies and everyday objects. Now let's consider what happens when a body is thrown upwards. It rises to a certain height, but then, due to Earth's gravity, it starts to fall back down. Gravity is what pulls objects toward the center of the Earth, and this force is what keeps everything grounded. Moving beyond Earth, let's talk about attraction in outer space. The gravitational pull extends far beyond our planet. For example, there's a clear attraction between the Earth and the Moon. This is what causes the Moon to orbit Earth. Similarly, the Sun exerts a gravitational pull on all the planets in our solar system, keeping them in their orbits. These gravitational forces are fundamental to understanding not just how objects move on Earth, but also how celestial bodies interact across space. They remind us that gravity is a universal force, connecting everything in the universe. This interconnectedness is a key part of the overall picture we're exploring today. When a body moves along a circular path, it's constantly changing its direction. Now, this change in direction means there's a force acting on the body, right? And that force always points toward the center of the circle. We call this the centripetal force. It's what keeps the body moving in that curved path instead of flying off in a straight line. If, for some reason, this centripetal force were to disappear, the body wouldn't stay on the circular path. Instead, it would just go straight, tangent to the circle at the point where the force vanished. So the key idea here is that the centripetal force is essential for circular motion. It's what continuously pulls the body toward the center, maintaining that curved trajectory. Without it, the motion would become linear, and the circular path would be lost. This concept ties back to our overall theme of understanding forces and motion, highlighting how specific forces govern the paths objects take in nature. So on this slide, we're looking at the universal law of gravitation. This law states that every object in the universe attracts every other object with a force. Now, what's really fascinating is how this force depends on two key factors. First, it's directly proportional to the product of the masses involved. That means, the bigger the objects, the stronger the gravitational pull between them. Second, it's inversely proportional to the square of the distance between these objects. So the farther apart they are, the weaker the force becomes, and this decrease happens quite rapidly due to the square relationship. This concept helps us understand why planets stay in orbit around the Sun and why objects fall to the ground on Earth. It's a fundamental principle that connects all objects in the universe, illustrating the universal nature of gravity. As we move forward in this presentation, keep in mind how this law underpins many astronomical and physical phenomena we observe every day. Now, let's talk about why the universal law of gravitation is so important. This law did something remarkable. It explained many phenomena that people once thought were unconnected. For example, it helped us understand the force that keeps us firmly attached to the Earth. Without this law, that force would seem mysterious. It also explained the motion of planets around the Sun, which is a fundamental aspect of our solar system's stability. Additionally, it clarified how the Moon orbits the Earth, creating the tides we observe regularly. And speaking of tides, the law describes how the gravitational pull of the Moon and the Sun influences their rise and fall. Overall, this law was a breakthrough because it connected these phenomena under a single, universal principle, illustrating how gravity acts everywhere in the universe. It's a key piece in understanding the larger picture of how celestial bodies interact and move. Let's talk about free fall. When we think about objects falling towards the Earth, the main force at play is gravity. The Earth pulls objects towards it with this force, which is what causes things to fall. Now, when an object is falling solely because of this gravitational pull, without any other forces like air resistance significantly affecting it, we call that free fall. It's a fascinating concept because it helps us understand how gravity works in a very pure form. This idea connects to the overall theme of exploring forces and motion, giving us a clearer picture of how objects behave under the influence of gravity alone. When an object falls towards the Earth, its acceleration isn't constant in the way we might initially think. Instead, it changes due to the gravitational force exerted by the Earth. This specific acceleration is what we call the acceleration due to gravity, or gravitational acceleration. You'll often see it denoted simply as g in equations and diagrams. Now, the unit for g is the same as that for acceleration in general, meters per second squared, or ms2. Understanding this concept is crucial because it links directly to how objects move under gravity, which is fundamental to grasping the laws of motion and the forces at play in our universe. So, whenever we analyze falling objects or projectiles, this acceleration due to gravity is a key factor we always consider. Now, let's take a closer look at the mathematical expression for gravitational acceleration, which we denote as g. This formula is fundamental because it quantifies the acceleration experienced by an object due to Earth's gravity. The key components of this expression include the gravitational constant, which is a universal constant, the mass of the Earth, and the distance from the center of the Earth to the object. What's really important here is understanding how these variables interact. For example, as the distance from Earth's center increases, the gravitational acceleration decreases. This helps explain why objects weigh less the higher they are above the surface. Connecting this to our overall theme, this formula not only describes the force acting on objects, but also lays the groundwork for understanding many phenomena in physics, from planetary orbits to satellite technology. It's a simple yet powerful expression that captures the essence of gravity's influence in our universe. Now, let's take a closer look at the factors that affect the value of g as you move from the poles toward the equator. The Earth's radius actually increases, and this causes the value of g to become greater at the poles compared to the equator. In other words, gravity is slightly stronger at the poles. Additionally, as we go to higher altitudes or larger heights above the Earth's surface, the value of g decreases. This is because gravity weakens as the distance from the Earth's center increases. These variations are important to understand because they influence how objects behave at different locations and elevations on Earth. Understanding these factors helps us grasp the dynamic nature of gravity and its dependence on Earth's shape and size. Now, let's look at how we calculate the value of g, the acceleration due to gravity. First, we need to consider the universal gravitational constant, g, which is 6.7 times 10 to the power of minus 11 Newton meter squared per kilogram squared. This constant tells us the strength of gravity between two masses. Next, we look at the mass of the Earth, which is approximately 6 times 10 to the 24 kilograms, and the radius of the Earth, about 6.4 million meters. These values are crucial because they directly influence the gravitational pull that gives us our value of g. When we put all these values into the gravitational formula, remember, the one that relates the force to the product of the masses divided by the square of the distance, we can calculate the acceleration due to gravity at the Earth's surface. This step is essential because it connects the fundamental constants and Earth's properties to the gravity we experience daily. It also highlights how the universal law of gravitation underpins our understanding of gravity here on Earth. Let's take a closer look at the differences between the gravitation constant, g, and gravitational acceleration, g. Starting with g, its value is 6.67 times 10 to the power of minus 11 Newton meter squared per kilogram squared. It's important to remember that g is a scalar quantity, meaning it has only magnitude and no direction. Its value remains constant everywhere in the universe, which makes it a universal constant. This consistency helps us understand gravitational interactions on a cosmic scale. The unit of g is nm2/kg2, reflecting its nature as a proportionality constant in Newton's law of gravitation. Now, moving on to g, the gravitational acceleration. Its value on Earth's surface is approximately 9.8 meters per second squared. Unlike g is a vector quantity, so it has both magnitude and direction, pointing toward the center of the Earth. Unlike g, the value of g can vary depending on your location. Elevation, latitude, or local mass distributions can cause slight differences. Its unit is meters per second squared, aligning with it being an acceleration. So, in summary, g is a universal constant, scalar and unchanging, while g is a local acceleration, vector, and can vary from place to place. Understanding these distinctions helps us grasp the broader concept of gravity and how it operates both universally and locally. Let's take a closer look at the equations of motion for a falling object. Imagine an object starting to fall towards the Earth with an initial velocity u as it falls. Gravity accelerates it downward at a rate g after covering a certain height h in time t. Its velocity has increased to v. The first key point is the equation for velocity after time t, which is v equals u plus gt. This makes sense because the velocity increases linearly with time due to constant acceleration. Next, the height covered in that time t can be expressed as h equals ut plus 1/2 times gt squared. This equation shows how the initial velocity and the acceleration contribute to the total displacement over time. Finally, there's a relation between the initial and final velocities that excludes time. V squared equals u squared plus 2 times g times h. This equation is particularly useful when you want to find the final velocity without knowing the time taken. These equations are fundamental because they connect velocity, displacement, and acceleration in a clear way, helping us understand the motion of objects under gravity. They form the backbone of classical mechanics and tie directly into the overall theme of understanding motion in a gravitational field. All right, let's look at this important point. When we're talking about the acceleration due to gravity, which we denote as g, its sign depends on the direction of the motion relative to Earth. If an object is moving towards the Earth, we consider g as positive. Think of it as gravity pulling the object downward, reinforcing the direction of motion. Conversely, if the object is thrown in the opposite direction, away from the Earth or upward, we take g as negative. This sign convention helps us keep our calculations consistent and clear. It's a simple but crucial detail that connects to the broader theme of understanding motion and forces in our study. Remember, the sign of g indicates the direction of acceleration, which is fundamental when analyzing different types of motion. Let's talk about mass. Mass is essentially the amount of matter that makes up a body. It's a fundamental property because it tells us how much stuff is inside. Now, this mass is directly related to inertia, which is the resistance an object has to changes in its motion. So the more mass an object has, the more inertia it possesses, meaning it's harder to start moving or stop moving. One important point to remember is that mass is constant. It doesn't change depending on where the object is. Whether you're on Earth or somewhere else in the universe, the mass remains the same. And of course, the SI unit used to measure mass is the kilogram, or kg. Finally, it's worth noting that mass can never be zero because that would mean there's no matter at all, which isn't possible for any physical object. So, understanding mass helps us grasp how objects interact and resist changes in their motion, tying into the broader theme of understanding physical properties and their effects in the universe. Let's talk about weight. The weight of a body is essentially the force with which the Earth attracts it. Now, this force depends on two main factors: the mass of the body, which we denote as m, and the acceleration due to gravity at that location, which we call g. The relationship is quite straightforward. F equals m times g. Since weight is this force, we can say that the weight W is also equal to m times g. An important point to remember is that gravity, g, is considered constant at a given place. Therefore, weight is directly proportional to the body's mass, meaning if you increase the mass, the weight increases proportionally. But here's an interesting aspect. Because gravity varies from place to place on Earth, the weight of an object can change depending on where you are. For example, an object weighs slightly less at the poles compared to the equator. And finally, the SI unit for weight is the same as that for force, which is the Newton, abbreviated as ENSO. In essence, weight is a force resulting from gravity acting on a mass, and understanding this helps us see how weight can change with location and mass. Let's take a closer look at the difference between mass and weight. First, mass is a scalar quantity, which means it has only magnitude and no direction. It remains constant regardless of where the object is located. We represent mass with the letter m and measure it in kilograms or kg using instruments like a beam balance. On the other hand, weight is a vector quantity, meaning it has both magnitude and direction. It depends on the position of the object, specifically on the gravitational pull at that location. That's why weight can vary if you change the object's position, such as moving from the Earth's surface to a higher altitude. We denote weight with W and measure it in newtons, using tools like a spring balance. The relationship between weight and mass is given by the formula W equals m times g, where g is the acceleration due to gravity. Conversely, if you know the weight, you can find the mass by dividing W by g, using the formula m equals W divided by g. Understanding these differences is important because it helps us grasp how objects behave under gravity and how we measure them accurately in different contexts. Let's talk about the weight of an object on the surface of the moon. So, the weight we usually think of is the force with which Earth pulls on an object. When we move to the moon, that force changes because the moon's gravity is weaker. The key point here is that the moon's mass is much less than Earth's, which means it exerts a smaller gravitational pull on objects. Now, it's important to understand that an object's mass stays the same whether it's on Earth or the moon. But its weight, which depends on the gravitational force, differs. So, even though the object itself doesn't change, how heavy it feels varies depending on the celestial body it's on. This is a great example of how gravity influences weight, and it helps us understand the differences in gravitational pull across different planets and moons. Now, let's take a closer look at the mathematical expression for the weight of an object on the surface of the moon. The weight of an object, as you know, depends on the gravitational pull exerted on it. This is different from mass, which remains constant regardless of location. The formula we use is straightforward. Weight equals the mass of the object multiplied by the acceleration due to gravity at that location. Specifically, on the moon, this acceleration due to gravity is much less than on Earth, roughly 1/6. So, if we denote the weight as W, the mass as m, and the moon's gravitational acceleration as g, then the equation becomes W equals m times g. Understanding this helps us see why objects feel much lighter on the moon, and it's a key concept when studying gravitational effects and space exploration. It connects directly to the overall theme of how gravity influences objects in different environments. All right, let's continue. As we move forward, I want to emphasize that understanding these key points is crucial for grasping the bigger picture. First, it's important to recognize how each element connects to our overall theme of growth and innovation. These concepts build on what we've discussed earlier, showing how strategic planning and adaptability play vital roles. Remember, the core idea here is to keep evolving and stay ahead of the curve. By focusing on these aspects, we can ensure sustained success and resilience in a constantly changing environment. So, keep these points in mind as they form the foundation for the next steps in our journey. Continuing on, I want to emphasize that this is just the beginning. There's a lot more to explore and understand as we move forward. The key points we've covered so far set a solid foundation, but it's important to keep in mind that these concepts are interconnected and build upon each other. As we progress, we'll see how each element influences the next, creating a comprehensive picture. Remember, the overall theme here is about growth and adaptation, so staying flexible and open to new ideas is crucial. So, let's keep this momentum going and dive deeper into how these principles can be applied in real-world scenarios. So, to wrap things up, the key idea here is that the weight of an object on the moon is actually only about 1/6 of its weight on Earth. This is because the moon's gravity is much weaker than Earth's. What's important to remember is that we can find this ratio by using the values we've looked at earlier in the table. By comparing the weights on the moon and on Earth, we can see exactly how much less gravity affects objects there. This concept ties back to our overall theme of understanding gravity and how it varies across different celestial bodies. It's fascinating to see how these simple calculations give us a clearer picture of the differences in gravitational pull, isn't it?